Hello and welcome to another exciting lesson in chemistry. Today we'll be talking about calculating delta H from heats of formations. This one won't be as long as Hess's law because it's a little bit more straightforward uh, process. So today we'll be talking about calculating delta H from heats of formation. And remember, delta H is enthalpy, and enthalpy is a state function, meaning it doesn't depend on the path, just the initial and final states. And so we've talked about calculating delta H by knowing the heat of the reaction and the moles involved. We also last time discussed delta H when referring to Hess's law. That's another way you can calculate delta H. But today we're going to look at what's called the heats of formations to calculate delta H. And so the heat of formation is the enthalpy change when 1 mole of pure substance is formed from its elements. So what does that mean? That means, for example, if we have nitrogen gas plus hydrogen gas, and we produce ammonia. So first we have from its pure elements, so nitrogen is commonly a gas, hydrogen is commonly a gas, but we only need to form 1 mole of product. So this would need to be 1/2 N2 and 3/2 H2. And this would be an enthalpy of formation reaction because we have elements in their standard state. So again, nitrogen is naturally occurring as a gas, hydrogen is naturally occurring as a gas, and we only form 1 mole of product. And the reason that the reactants have to be in their standard state is because if we look at the second bullet, elements in their most stable physical and chemical form have a heat of formation of 0. So since nitrogen in its most stable form is N2 gas and hydrogen is H2 gas, these heats of formation are 0. So whatever heat is consumed or produced in this experiment is the result of the formation of NH3. Now, if we were to write a different equation, say we wrote N2 gas plus H2 gas yields NH3 gas. Now let's say we're going to put a 2 here and a 3 here. Now this second equation would not be a heat of formation reaction. And the reason is because we still have our elements in their stable form. However, we produce 2 moles of product, not 1. So this would not be a heat of formation reaction. Another example of this, we look at the third reaction. Again, this would not be a heat of formation reaction because we do form 1 mole of product, but it comes from elements in their non-stable form. So nitrogen liquid and hydrogen solid are not the most stable forms of these 2 elements. This would not be a heat of reaction equation. So again, for heat of reaction equations, you need to form 1 mole of product from its elements in the most stable form. And so the reason is because elements in their most stable form, this includes diatomic elements and regular elements, is the heat of formation is 0 for elements in their most stable form. So for example, O2 has a heat of formation equal to 0, but ozone, which is another form of oxygen, heat of formation is greater than 0 because it's not the most stable physical form of that. And so now to calculate the heat of a reaction, you need to sum up the heat of formation of products and subtract it from the sum of the heat of formation of reactants. And again, products are the final state, reactants are the initial state. So we'll look at a few examples involving that. Let me just clean up my board here. So first example, we have carbon plus oxygen gives us CO. Again, we look up the heat of formation of CO is negative 110.53. Again, heats of formations come from tabulated values. So if you look in your chemistry book, in one of the appendixes, they'll have all the heat of formations of different compounds. Now, the heat of formation of carbon solid is 0. That's not a good 0. The heat of formation of carbon solid is 0. And the heat of formation of O2 gas is 0. So therefore, again, it's products minus reactants. And so you have to multiply the heat of formation by the coefficient in front of the reactant or product. So again, this heat of formation is for 1 mole of CO, but we have 2 moles. So we take 2 times the heat of formation, and then we subtract it from the reactants. Both of these are 0. So we get the delta H of the reaction. And in this case, it's exothermic. So again, it's the products minus the reactants. Again, you multiply the heats of formation by the coefficient in front of the product or reactant. Here's another example. We have ammonia plus oxygen gives us steam and nitrogen monoxide. And so here, this is actually a combustion reaction. Remember, combustion reactions are exothermic. So this means that when we calculate delta H, it should be negative. So what we're going to do is we take the products. We're going to take the heat of formation of each product. And by the way, make sure you look up the heat of formation of H2 gas, because H2 liquid, as we'll see in a second, has a different heat of formation. So different physical states have different heats of formation. Only the most stable physical state has a heat of formation of 0 for elements. But for compounds, different physical states have different heats of formation. So we're going to take the heat of formation of steam, multiply it by 6 because the coefficient of 6 there. We're going to take the heat of formation of nitrogen monoxide, multiply it by 4. We're going to add these two up and subtract it from the heat of formation of reactants. So we're going to take the heat of formation of ammonia gas, multiply it by 4 because, again, 4 is in front of ammonia, and take the heat of formation of oxygen, multiply by its coefficient, which is 5. Now, since oxygen gas, O2 gas, is its stable form of oxygen, the heat of formation of oxygen would be 0. So now we look up the heats of formations. Again, these heats of formations are going to be given to you in a problem, or you have to look it up in a book. Now, one of the most common mistakes in calculating heats of reaction is this heat of formation is negative, and you're subtracting it. So 2 negatives make a positive. So again, you see that the heat of formation is multiplied by each of the coefficients from the reaction. We'll simplify a few terms. We get this. Notice that this became positive because, again, a negative and a negative make a positive. Most common mistake, students forget that, and they keep it negative. Most common mistake. And then we add everything up, and we get the delta H of reaction is a negative 905 kilojoules per mole. So that makes sense. We said it would be negative. It is negative because, again, combustion reactions are exothermic reactions. That's why your grill gets hot when you can, on a gas grill, when you cook your steak. So I'll give you a few seconds to look at this over, and then we'll move on to the next slide. So this is just an excerpt of the heats of formations, and these usually come from an appendix. And typically, in the appendix, there are going to be 3 columns. There's going to be a heat of formation column, a molar entropy column, S naught, and a Gibbs free energy column. And what we're looking for here is the heat of formation column. You'll use the other 2 columns if you take Gen Chem 2, but we're interested in the heat of formation column. And the heats of formations are given in kilojoules per mole. So make sure you get the right column when you look it up in the appendix. Typically, it's Appendix 2 or Appendix B in a textbook. And the heats of formations are determined at standard temperature, which is 25 degrees Celsius. And so a few things I want to point out is, if we look at bromine liquid and bromine gas, we all know that bromine naturally occurs as a liquid. That's why its heat of formation is 0, whereas gas is it's not the stable form of bromine, so it has a heat of formation. And it makes sense when you go from a liquid to a gas, you have to absorb energy, so that's why you have to absorb heat to convert 1 mole of bromine liquid to 1 mole of bromine gas. Secondly, we look at carbon. Carbon has 2 forms, carbon graphite, carbon diamond, and based on the heats of formation, you see that carbon graphite is the stable form of carbon. So if you apply heat to carbon, you can convert it to diamond. So it's an endothermic process to convert graphite to diamond. One last one we want to look at is I2 solid, I2 gas. We know that I2 solid is a standard form of iodine, and to convert it to gas, so it sublimes, it takes 14.9 kilojoules of heat. Now, I'm not sure these are the right heats of formation. I might have copied it wrong, because if you look it up in the book, these are a little bit different. But the fact is that iodine standard form is solid, iodine gas is a non-standard form. So iodine solid would have, I2 solid would have a heat of formation of 0, I2 gas a non-zero heat of formation. Again, these can be found in, it's usually Appendix 2 or Appendix B, and you want the column that says delta H of formation. Now let's look at some problems. So here we have a combustion reaction. We have a fuel plus oxygen gives us oxides of the fuel. So here, delta H should be negative, because again, it's a combustion reaction. So the first thing you need is always a balanced chemical equation, which is what we have. And then you need to look up the heats of formations. Again, O2 is 0 because it's in its standard form. And then we look up the other heats of formations from the table. So we set it up. Again, the coefficients are multiplied by the heat of formation. So 2S2O, 2SO2, 2 is multiplied by the heat of formation. 2 moles of steam multiplied by the heat of formation. Again, oxygen is 0, and then H2S we multiply by 2. So again, a negative and a negative will make a positive. So negative 40.4 minus, they become positive. We get the delta H of reaction. And again, it's exothermic, just like we predicted, because it's a combustion reaction. Next up, we have a reaction involving methane and chlorine, gives us carbon tetrachloride, HCl. It's unbalanced. So the first thing you need to do is balance it. And also, in the meantime, you need to look up the heats of formations of your reactants and products. Notably, look that Cl2 gas is a stable form of chlorine, so it has a heat of formation of 0. Again, you get these heats of formations from the appendix or a table in the book. If it's a problem, typically they give you the heats of formation. So we balance it, and I know I didn't balance it correctly. Let me correct it. There should be a 4 here. So it should be 4 Cl2. It's not going to affect the problem because, again, the heat of formation of chlorine is 0. So again, this should be a 4. There. Now we combine terms and we'll solve for the heat of reaction. So again, 2 negatives make a positive. And we see it's exothermic. So what this means, when something is exothermic, it means the bonds in the products are more stable than the bonds in the reactants. So the products here are more stable than the reactants. Give you a few seconds to look this over, and then we'll move on to the next example. So these are some straightforward heat of reaction problems. We'll give you the equation, look up the heats of formations, determine the delta H of reaction. This one's a little bit different. So let's read this over. We want to find the standard enthalpy of formation for ethylene. So we want to determine what ethylene's standard enthalpy of formation is. Given the following data, it gives us the heat of combustion. So the heat of combustion is of C2H4 is negative 1411 kilojoules per mole, and we have the heat of formation of CO2 and H2O. Notice the heat of formation of O2 is not given because, again, it's in its natural state. It has a heat of formation of 0. So what we're looking for is the delta H of formation of C2H4. That's what we're looking for. Now we have an unbalanced equation, so we do need to balance it. So let's start balancing the equation. So we have 2 carbon, we need 2 carbon here. So we'll put a 2 in front of CO2. Now we have 4 hydrogen. We need a 2 in front of H2O. We have a total of 6 oxygen, so we need a 3 in front of O2. Let me do that better. So 3 in front of O2, 2 in front of CO2 and H2O. Now the equation is balanced. So we know what the heat of combustion is, so the delta H of combustion is the same thing as the delta H of reaction. It's just that in this case, this reaction is a combustion reaction. So we know this is given to us, negative 1411 kilojoules per mole of ethylene. Oops. So that we know. We know the heats of formation of CO2 and H2O. Now we write this out. We have negative 1411 equals products. So we have 2 times the heat of formation of CO2 gas, negative 393.5, plus 2 times negative 285.8, the heat of formation of steam. all of this minus the heat of formation of C2H4. Because remember, O2 is 0. So something minus 0 is still something. So now we need to solve for the delta H of C2H4. So let's rearrange some things here. Or let's simplify. Negative 1411. So negative 1359 minus delta H of formation of C2H4. And this becomes negative 52 equals negative delta H formation of C2H4. Now we get rid of the negative sign, and we see that the delta H of formation of C2H4 is 52 kilojoules per mole. So that's the heat of formation of C2H4. Go on to the second example. So here we have a reaction involving acetylene. In the presence of excess oxygen, generates gaseous carbon dioxide and water. It gives us the heat of formation of CO2 gas, H2O gas, and acetylene. It wants to know how much energy is released. So that means it's going to be negative in kilojoules when we react 273 grams of acetylene. So what we have to remember is that delta H of reaction is Q divided by N, so therefore Q equals delta H times N. So in order to calculate Q, we need the delta H of reaction and we need N. Again, N is number of moles. So we can find the number of moles. We have N and we know the mass. So mass divided by molar mass gives us moles. 28 grams per mole. .75 moles. So we have the moles of acetylene used. Now we got to find the heat of reaction, delta H of reaction. So the way we got to do that is we got to write the chemical equation and balance it. So we have C2H2 gas plus O2 gas yields CO2 plus H2O gas. So since we're wanting to determine how much ethylene is burned, we want to keep the coefficient of ethylene 1. So we have 2 carbon on the reactant side. We want to make 2 carbons on the product side. So we put a 2 in front of CO2. Now again, the reason we want to make acetylene have a coefficient of 1 is because we're looking for how much acetylene is burned. So if we can find the delta H in respect to 1 mole of acetylene, that'll make it easier for us because then we can just multiply the number of moles by the delta H. So in order to make this, keep this 1, we have a total of 5 oxygen. So our hydrogen are balanced. We have a total of 5 oxygens. So this would be 5 halves O2. So O2, we need a coefficient of 5 halves. So now this is balanced where we kept the coefficient of acetylene as 1. So now we can calculate the delta H of reaction. DH of reaction. You could call it delta H of combustion too, because it is a combustion reaction. We have 2 times negative 393.5 plus 2 times negative 8 subtracted from 226.6. That's negative 1271 minus 226.6. And we get negative 1497 as delta H. Kilojoules per mole of acetylene. Because there's only 1 mole of acetylene. Let me just double check my work. Looks right. So now this is the delta H of reaction. And now we have the delta H of reaction. The moles, we can calculate how much energy is released. So Q equals 14,600 kilojoules. Negative, actually, sorry. Forgot the negative sign. So that's how much heat is released when 273 grams of acetylene is burnt. Give you a few minutes, a few seconds to look that over. All right. And one last example. Here we have the combustion of glucose. The enthalpy of combustion of this reaction is negative 2,801 kilojoules per mole. What's the heat of formation of solid glucose? So what we need to do here is determine what the heat of formation of glucose is, given the information provided. So let's set up. So our reaction is balanced. So we have 1 mole of glucose, 6 moles of O2, 6 moles of CO2, 6 moles of H2O. So heat of reaction So the delta H of combustion equals the delta H of reaction, which equals negative 2801 kilojoules per mole. So we have delta H of reaction six times negative 393.5 plus 6 times negative 285.8. So notice here that the heat of formation of steam and water are different. So if you remember, steam was negative 241, water is negative 285. And now what we're looking for is the heat of formation of glucose. We got a oh, excuse me, not one, my bad. So let's simplify this. Snapperoo. So we get this equals negative 4,076. We just double check. Yep. Minus the delta H formation of glucose. So now we get 1275 equals the negative delta H formation of glucose. Oops, misspelled it. Now we just switch the sign. So every mole of glucose formed releases 1275 kilojoules. So while you look at that, I'm just going to double check my work. And yes, I did get the answer. Same for heat of combustion. So on that note, that concludes determining enthalpy of reaction using heats of formation, and that also concludes our thermochemistry chapter for us. That note, we'll see you next time.